Okay. Okay. So welcome to the last lecture on flavor physics, and thanks for sticking out until the end. So yesterday we finished off with the realization that flavor measurements are a sensitive probe of new physics. Okay, I didn't write it out, so. And in particular, what we looked at in some detail was sensitivity of delta F equal 2 observables. And we realized that the most sensitive ones come from the kaon sector. In particular, CP violation in KK bar mixing is probing new physics scales up to a few times 10 to the 5 TeV. And we also try to understand why this hierarchy of different flavor transitions in their sensitivity, and it's all coming back due to the particular structure of the CKM. So the question that we can ask is there a way? So this is what we call the new physics flavor puzzle, and a question that we can try to address is there a way to systematically try to soften this pressure on new physics being either very heavy or having very suppressed couplings for some reason. And one possibility, which is based upon exactly the systematic exploration of the symmetry structure of the flavor in the star model, goes under the name of minimal flavor violation. And the main premise of this is to require that all flavor violating interactions, even beyond those in the star model, are sourced by the same flavor structures as in the star model, so they can be expanded in terms of the star model Yukawas. So flavor violating interactions are somehow linked to known Yukawa couplings we've shown this explicitly for the standard model, but now we will require this to be true even beyond the standard model. Okay, so to do this, we can actually explore the same procedure that we already did in the standard model. So we just start with the flavor symmetry of the standard model before introducing flavor breaking. So the flavor symmetry which will be, at least in the quark sector, this will be SU3 cube. I left out the U1 factors. And the second ingredient is to introduce the number of flavor breaking structures into this theory. So set symmetry breaking terms. Okay. Now this looks to be still completely general. So whatever new physics with flavor indices I introduce, I can always satisfy these conditions. Okay. So the flavor symmetry is always SU3 at least, because I have the Star model fermions, which in the quark sector there are 3 sets of fermions. And so, and I can always introduce some set of symmetry breaking terms. But the crucial ingredient to minimal flavor violation is now to require that these symmetry breaking terms can be written as a well-behaved expansion in the Yukawas. So that is a strong constraint on the model building, that the only symmetry breaking structures that are there fundamentally are the up and the down Yukawas, again in the quark sector. Okay, so these are the representations, the spurious representations under the SU3Q, SU3U, and SU3D flavor symmetries of the Star model. Now we can do this. We can make this tractable. So in general, if the up and down Yukawas were completely random 3x3 complex matrices, then higher powers of those would just give other completely arbitrary looking matrices. So it would not be of big help to do it. No? But we can actually explore the hierarchical structure of the Yukawas to make this very well behaved expansion, because, so this is tractable. Due to peculiar structure of Star model flavor. In particular, if we consider higher powers of these Yukawas, so we'll be building larger structures, but just doing products of these Yukawas. And in fact, there is even a theorem which says that any flavor breaking of any structure can be constructed out of a finite set of high order products of the up and the down Yukawas only. Okay. I will not elaborate in detail, because this is in general will still not be a minimal flavor relation, because in this finite expansion, this high order terms will sometimes come with ridiculously high coefficients, expansion coefficients. But I will stick to the expansion of minimal flavor relation, where this expansion of higher powers is supposed to be well behaved. So the coefficients of the Taylor expansion, if you want, are always order 1 or smaller. And so why this is tractable is because if we consider higher powers of the Yukawa, in particular, the largest eigenvalue of the Yukawas corresponds to the top Yukawa. So the largest contribution to any structure will come from powers of the up Yukawa matrix. And if we compute this to some nth power, for example, this is just one of the structures that we can build. And we consider flavor violating terms of this. So when the indices so we look at for off-diagonal terms in this product. To a good approximation, we can write them as just lambda top to the nth power times VTI star VTJ. Okay. Yeah. Oh, so I would have to look up the name who did it. Yeah, there is a mathematician which showed that if you have a certain set of matrices, you can expand any other matrix in a finite set of these matrices. Okay. It's just a matrix theorem. It's nothing to do with physics a priori. It's just an application of this. We can do it in this case. Okay, so this means that we can actually, in a way, resum And remember, the top Yukawa is order 1. Okay, so this higher powers of the top Yukawa will just give you higher powers of 1, so it's just 1. So any arbitrary power of such products will just give same flavor structure. Okay, so this allows for a very simple summation of this kind of terms. Okay, and in particular, there is an immediate consequence that we can write down. If you now write the amplitude for meson-anti-meson oscillations, so we think of some neutral flavored meson oscillating into its anti-flavor eigenstate. In such minimal flavor violating, in presence of minimal flavor violating new physics, we can write it as VTI, VTJ star, or VTI star, VTJ, sorry, squared times the same amplitude in the standard model, where I just factored out the CKM prefactor. So this amplitude now contains the loop factor and the operator, okay, the Lorentz-Carroll structure. And then I get that, so the standard model value is just this, and then the new physics contribution I can parameter adjust with C2. This is the same C2 that I wrote yesterday. So in the slides it's Z. Okay. And then yesterday we showed that the standard model prefactor is roughly 64 pi squared times V squared. This would be the value of the loop in the standard model. And here we have this is to be compared with the new physics scale lambda. Okay, so what we achieve in this way is that we factor out the CKM prefactor, so the new physics would now naturally suffer the same flavor suppression as the standard model. So these sets of flavor constraints now in presence of minimal flavor violating new physics looks completely different. Okay, so instead of having the kaon sector being the most stringent, in particular the CP violation in the kaon sector being the most stringent constraint on such models, okay, this is the same plot, but now fixing the scale at 1 TV, and this just tells us that if we want some new physics at the TV with generic flavor, then its couplings in the flavor changing couplings in the talking to the first two generation should be tiny, especially in presence of phases. CP-odd phases. Now, in case of minimal flavor relating new physics, this now looks completely different, yes? Lambda squared, yeah. Thank you. So now it looks completely different. In particular, since these, once we factor out the flavor structure of new physics, the remainder is actually a Hermitian operator. And since it's a Hermitian operator, this coefficient is actually required to be real for this particular chiral structure, okay? For this operator, which is the same as in the standard model. So all the phases, all the CP-odd phases are already in the CKM prefactors. So what we achieve for minimal flavor relating new physics is that it's flavor aligned with the standard model, but also it's CP aligned with the standard model. So it has exactly the same CP phase, okay? Which means that all CP violating observables become transparent. It becomes transparent to CP violation, okay? We don't see any effects in CP violating observables. And so what is left is of course, for example, a meson oscillation frequency measurements. And so we see that contrary to the kaon system now, the most stringent constraint comes from the B sub S system. And this, now you can also understand why, because I told you that we have the best theoretical understanding of the standard model contributions in the B and the B sub S system, where the precision that we are able to reach is approaching a % level, whereas in the Count system, it's limited by theoretical uncertainties at a 10% level. Okay, so this is actually no. It's in the case of delta mk, it's much worse. It's order 1, right? Yeah. So if we have now new physics, which is minimal flavor violating, or in fact, you can somehow relax this construction with the observation that actually to get rid of the stringent Count constraints, you don't need really to really fully respect the standard model flavor breaking structure. The most relevant constraint comes from the fact that the standard model Yukawas, if you really look at from just in a very coarse-grained way, the up Yukawa will roughly look like this. Okay, it's just zeros, and there's just the top Yukawa. Okay, and now you can say, okay, so what is the approximate flavor symmetry breaking in the standard model? Well, it looks like it's basically S3 breaking to a U2 cross U1. Okay, so in fact, any model which will respect this will be automatically protected from dangerous KK bar mixing constraints, because it's the approximate U2 symmetry of the first two generations, being that their masses are very small, which actually protects chaos mixing from large flavor changing neutral currents. Okay, so that's why in the more recent literature you will often come across U2 models, because they just pick the more interesting, the most protective aspect of minimum flavor relation, but allows for a more general model building. Okay. It's just a side note on the literature. Okay. So this was so one last comment is that you in such models. So this is true for both minimal flavor relating models, but also for more general U2 models. Is that now we actually expect the first signs of new physics in flavor to come in B physics. Okay, no longer in charm and Count physics, but in B physics, which will become very important soon. Because now we will switch and start to discuss new physics in delta F equal 1 flavor observables. Sorry? Yeah, it has to be real. Yeah, from hermeticity. So if you write this, the operator which sources this in the SU2 invariant form, it's basically Q bar Q gamma mu squared operator. Now, if QQ bar are the same field, then this is Hermitian. Yeah? And in general, this would not be true. So if you had some general flavor structure here at Cij, Ij, these are not the same fields. So this is no longer necessary to be Hermitian, so this can be complex. But now, since we expand in the Yukawas, this is now just a triplet of flavor. And this is also a triplet of flavor, so of SU3Q. So these are actually the same object. And all the flavor and CP structure is in this matrix, which is related to the CKM and shares the phase. Okay, that's... So this is only about when you are talking about delta equals 2. Yeah, exactly. Yeah. There are certain statements that you can make also for delta F equal 1, but are more involved. Okay, there is no such simple statement. So you cannot forbid CP evaluation completely in delta F equal 1. You can just relate different processes among each other in case of delta F equal 1. Yeah, okay. So now let's look at new physics in delta F equal 1 observables. And again, let me start immediately with the general parameterization of possible heavy new physics contributions. So we'll just write down a part of the effective Lagrangian contributing to such observables. So let me write the delta F equal 1 effective new physics piece. Okay, so yesterday we wrote a similar term for delta F equal 2. So what I will not discuss this in all generality with all the possible terms. I will just pick some of them which are most easily to understand and interpret, and you will see later why I chose those particular ones. So let me do, so the Wilson coefficient for the first one I will label Yij Q1 over lambda squared, and then in the SU2 invariant notation I will have the following operator QLJ phi dagger d phi. So for I being different from J, this is this operator changes flavor. Okay, we'll see what this does in a minute. Seems to be coupling to the Higgs, and in fact it's coupling to the Z. Then the, let me see. Yeah, and then I will also introduce, so there is a set of such similar operators where you can now change Q's for U's and D's. So for the electric isospin singlets. But what will be more interesting is perhaps to look at such operators, coupling quark and lepton currents. And again, I will have one. So first, let me write the other one as well, just to have both of them. YQ2 ij over lambda squared will be QL bar I gamma mu TA QJ times phi dagger d mu TA phi. Okay, so this is basically coupling a SU2 singlet current to an SU2 singlet Higgs current, okay, which would be a Z, and this is coupling a SU2 triplet quark current to a triplet Higgs current. But then let me introduce two additional operators which will come handy, which will be QL1. In general, this will have four indices, flavor indices, two on the quark side, two on the lepton side, IJKL over lambda squared, Q bar I, gamma mu, QJ times L bar K, gamma mu, LL. Okay, this is an operator coupling a quark current to a lepton current, and both of which flavor violating. And finally, I can also do the same for the triplet currents. So this will be QL2, again IJKL over lambda squared, Q bar I gamma mu TA QJ times L bar K gamma mu TA LL. And all of these can also have their Hermitian conjugates present. Okay. These are not all the operators one can write down, but these are the ones I will be discussing. There are more of them in general. Of course, TA are the SU2 generators. So what is the phenomenological consequence of a possible presence of such new physics operators? We can derive their effects, for example, in below the electroweak breaking scale, and just rewrite them. So below electroweak breaking, or after electroweak breaking, the first operator will become, so YQ1, And let me focus, for example, on the Kaon sector, just for concreteness. For first, so let me write out the flavor structure in the flavor changing contributions. So I have the contribution changing between S and D flavors times V squared over lambda squared times G over cosine of the weak angle times DL Z slash SL. Okay. And then we also have this similar things for the other flavor sector. So YQ1 BD times V squared over lambda squared G over CW DL bar Z slash BL. Again, CW is the cosine of the weak. Okay. Fine. Okay, we have the same thing again for BS sector, V squared over lambda squared G over CW SL bar Z slash BL. And we could also write this for the up sector, for example. We could just have, again, YQ1 CU V squared over lambda squared G over CW UL bar Z slash CL. And also for the top. Okay, I will not write down the first terms. As in the case of delta F equal 2, we can also try, so what this will do is this effectively generates couplings of Stannard-Model fermions to the Z, which are flavor changing, okay, DI, DJ. So these, which I showed you the first day, are in the first lecture, or maybe the second, that those are absent at tree level in the Stannard model, but they do appear at high orders in the weak expansion. So we can actually estimate the size of these in the Stannard model at one loop. Okay? And compare the sizes. Okay? And the contribution to such effective operators in the Stannard model come from the so-called Z penguins. So these are called so-called Z penguins. They appear at one loop. So you have DI, DJ, for example, and then again you have up-type quarks running the loop. And in the most interesting cases that we will discuss, namely this will be in B physics, these are dominated again by the top loops. So this is a top and a W. And then there is a Z going out. In B meson processes, of course, this Z is not on shell, so this will be virtual Z, which will then couple further to leptons or other stuff. And so we can compute effectively the value of YQ1 SD, for example, in the Stannard model. And it turns out to be, as expected, proportional to the top Yukawa squared over 64 pi squared, roughly, times VTD, VTS star absolute. Okay. So we can evaluate this quantity, and it's given by 5 times 10 to the minus 7. Okay. Which is bigger than the delta F equal 2 coefficient in the Kaon sector, because now we only have a single power of VTD VTS. In the delta F equal 2, we had 2 powers. Okay? That's why there we got a number like 10 to the minus 12. Here we have a number of 10 to the minus 7. Again, this is for the lambda Stannard model being V as before. Okay, this is the same, at the same scale. Okay, so we see that also in delta F equal 1, we will run into a new physics flavor problem if we don't do something about the flavor structure. But let's complete the exercise and also write this for the other sectors. At least the most interesting ones. So for example, YQ1 BD in the star model will be roughly y top squared over 64 pi squared times VTB VTD star absolute value, and this is of the order 10 to the minus 5. And finally, the YQ1 BS in the star model is roughly given by YT squared over 64 pi squared times VTB VTS absolute value, which is roughly 6 times 10 to the minus 5. Okay? So from these estimates, we can actually predict. Now, of course, you can do this much more carefully and actually compute the loop diagrams exactly and extract the dependence of the top quark and the W boson, as in the case of delta F equal 2. And such a computation then allows you to predict the corresponding rates of flavor violating neutral current mediated meson decays in the Standard model. In particular, in the SD sector, the most sensitive observable is the branching ratio of a charged kaon decaying to a charged pion and a pair of neutrinos. Okay? And this suppression coming from the flavor structure of the Standard model leads to a prediction for this branching fraction to be roughly 8 times 10 to the minus 11. Okay? Just a side note again, since here the final state is not a virtual Z boson, it's a pair of neutrinos, there is another contribution which contributes. So here, in addition to this diagram, in addition, one has box diagrams with the exchange of two W's. We have dj on one side, and then we have the neutrinos on the other side. So we have a top contributing in the loop and a charged lepton contributing in the loop. Okay. So only this combination is actually only one, which is gauge invariant. And they both contribute to, for example, to such a process. Okay. So the prediction of this rate, of course, requires the knowledge of the relevant hadronic matrix element again. So here we are not observing an S quark decaying to D quark, but a kaon to a pion. So again, we need some input from a non-perturbative QCD calculation, which can be done on the lattice. So one needs to evaluate, in particular, this matrix element between a pion in the final state and a kaon in the initial state. And the relevant current here is the flavor changing S to D current. Matrix element. Okay, so this is again, it's a 1-to-1 matrix element and can be computed with lattice QCD. Okay. QCD. In fact, such matrix elements are usually called where the initial and final state are not the same. They do depend on the momentum exchanged, the momentum flowing through the current. And so there are two functions which one needs to compute, and they're called, in this case, there are two functions one needs to compute, and they're called the form factors. Okay. Form factors. Okay. So yesterday we learned about the decay constant and the back parameter, which are relevant for B-bar mixing. In case of decay, the relevant hadronic quantities are usually the form factor, okay, in the seminatonic decays. Okay. So what about the other sectors? So let me see. So before going to the B, I probably have a plot. Yeah, okay. So you might think first that measuring a branching fraction which is smaller than 10 to the minus 10 is hopeless, but in fact they've observed these processes. There was a previous experiment, E787249, where they observed of the order of 10 events, actually it's less than 10, it's 7 events, when they were looking for this particular decay. And now there's actually a new experiment at CERN, which is running, and they're expected, so it's called NA62. NA62. And it's actually expected to measure this decay to up to 10% precision. So the first observation of this decay by the experiment was consistent with the standard model prediction, so was at the order 10 to the minus 10. And what you see here is the, due to large backgrounds, they measure in 2 distinct kinematic regions. So instead of the exchange momentum flowing through the current, they transform this into the relevant kinematic observable being the momentum of the pion. And the dependence of the rate as a function of this momentum, which you see here for the standard model, the red line, is actually given by phase space and by the behavior of the form factors. Okay? So the knowledge of the form factors is not just to know the normalization, but to also know the Q-square dependence, because this can affect the acceptance of experiments. This will become much more important when we come to B decays, because there it's not going to be as nicely behaved as here. Okay, so moving on to the B sector. Yeah, so what are the most sensitive probes of B to D and B to S, delta F equal 1 transitions of this form, of the Z penguin? I didn't write it down, no? No. So this is called the Z penguin. Okay. In this case, it's not the 7 leptonic decays at the moment, but they're purely leptonic decays. In particular, these one can predict the branching fraction of a B sub D decay to a pair of muons, for example. And this turns out to be roughly, again, 10 to the minus 10. And similarly, in the case of B sub S, one also predicts the B sub S decay to a pair of muons to be roughly 4 times 10 to the minus 9. Okay, so here, since we are looking at a leptonic decay, the relevant hadronic matrix element is now one which we are already familiar with, is DL bar, in the case of B sub D, for example, gamma mu, gamma 5, BL, B sub D, okay? And you know this is nothing else but P mu of the B times FB. Okay, is the decay constant of the B meson. Okay. Yeah. So this is 1 to 0 matrix element, and again, this is known now to a very impressive precision on the lattice. And why I put these two together, because when these two observables are searched for have been measured. So this one has been measured, and this one there seems to be an indication for it at the LHCb, and I hope I have, yeah. And this is the current experimental situation for these two decay modes. They're measured together because of the finite mass resolution of LHCb. They cannot really finally disentangle the B naught and B sub S peak in the dimuon invariant mass. So their most sensitive measurement actually just measures them combined, and there is a correlation between them, as you see in these contours, which are the experimental contours of the measurement. So the central value of the measurement is here, and it's at 1 standard deviation. It's consistent with the standard model prediction, which, as you see, is also quite precise in this case. Okay, so up to now, it seems the Flavour observables, also in the delta F equal 1 Flavour changing neutral current sector, seem to be quite consistent with expectations in the standard model. And we could, in principle, set bounds on possible new physics contributions. Now you could do this already alone because you already have all the ingredients. So let me just do it for the kaon sector, and then I will leave the B sub D and B sub S for your pleasure. So we can set constraints on new physics in delta F equal 1. In particular, if I choose the kaon observable, so k plus 2 pi plus nu bar, which now from experience, since I know that the standard model is mostly suppressed, most stringently suppressed in this observable, I expect the strongest bound for generic new physics to come from this decay. So the measured value of this decay mode at the moment, I mean, it's not yet discovered, so the uncertainty is order 1, just from the observation, times 10 to the minus 11. And from this, one can extract a constraint on this lambda new physics to be bigger than roughly this y, if we chose yq1 as d to be the relevant operator, 2 times 10 to the 2 TV, so 200 TV. Okay. So for order 1 Flavour changing structure in the SD sector, K2 pi nu bar again is probing scales over 100 TV. And from the measurements of the branching fractions for B sub S decaying to a pair of muons, which is 2.4 with an error of 9 times 10 to the minus 9, you can extract your own bound in the B to S sector, and similarly from the measurement or the bound on the decay of B sub D to mu plus mu minus, which is currently, so the measurement, if you want, is at 3 with an error of 2 times 10 to the minus 10, and you can again extract the bound on the relevant new physics contribution, okay, in the form of this Z penguin-like operator. Of course, this is not all the information that we can extract from delta F equal 1 observables. In particular, in the case of 3-body decays, in addition to the branching fraction, we have access to the whole angular phase space if we are able to reconstruct all 3 final states. This is not possible in K2 pi nu bar because we have 2 neutrinos which just escaped the detector. But it's possible in decays which are related to these leptonic B decays, just that we, instead of looking just at leptonic B decays, we look at semi-leptonic delta F equal 1 Flavour changing current mediated B decays. So let's look at them in more detail. So, of course, the hope here is that there are two goals to do this. First is that maybe by looking at the kinematical distributions, we could actually derive even more stringent bounds than just from the branching fraction. And the second hope is that while these leptonic decays probe only a certain linear combination of all possible effective operators contributing to them, we could maybe disentangle those contributions if we had access to more kinematical information. So there is more information available if you look at rare, so this meaning F's Flavor neutral current mediated, semi-leptonic modes. So here we'll be looking at the case where a B quark flavor changes to S and a pair of leptons, for example muons. Okay. So in terms of observables, we'll be actually considering B meson decays to kaons, which can, in practice, what will be interesting is to look at both pseudoscalar and also vector kaons and a pair of muons. Now you can immediately see why this is the wealth of information that is available by looking at these decays, because if you just go to the B meson rest frame, you can imagine now that the B meson decays to a virtual dimuon pair, where then, oops, sorry about that, which then flies off in some direction, okay, the two muons. And then on the other side, there is the K star, which is, in the case of, if you look just at the K star, it's also unstable and decays to a K pi final state. So we also have a K pi system on the other side, K pi. So there are many angles that one can define, and since my drawing skills are very limited, let me show you a nice drawing on the slide. Okay, so this is now the same system where where a B meson is decaying to a K star and a dilepton pair. So one can define three different relative angles, physical angles in this decay mode. One is the angle phi between the two planes in which the two leptons fly off and decay and the pi from the K star. And then, of course, there is the theta K star, which is basically, you can define it as the relative angle between the K star direction and the K-on direction, or the pi direction. You can choose one. And then also there is the theta L, which is the relative direction between the combined four-vector, the combined direction of the L plus L minus and one of the leptons. Okay? And so one can write down the complete differential. So this is now the, here it's written as a triplet differential. In fact, it's 4 times differential, because what is missing here is the dependence on Q squared, which is still there. So the depends on the momentum exchange, the momentum flowing through the quark current, if you want, or the dilepton invariant mass. Okay. But if you just focus on the angular distribution, the angular distribution can be completely worked out and has this form. Okay, so there are how many terms? There are 1, 2, 3, 4, 5, 6, 7, 8 independent terms. Okay, and each of these has a certain helicity amplitude associated with it, which has a hadronic part and a leptonic part, and the hadronic part has a Q square dependence, which again we need to describe with the hadronic matrix element between the initial B meson state and the final K star meson state. Okay. Okay. Yeah. So let me go here. So indeed, there seems to be a wealth of additional information available. If you look at now at differential, angular differential rates of semi-leptonic B decays, so one can attempt a differential rate analysis. Okay, in particular, looking at this distribution. Now here it turns out that this is much more theoretically challenging to predict than it seems at first glance. And so such observables have challenging, in general, they have challenging theoretical uncertainties. In particular, if we just consider the effective standard model Hamiltonian at the B scale, so at the scale of the B quark mass, so this is a scale where we've integrated out the W boson, the Z boson, the top quark. So all that's left is the B quark and all the lighters, so the charm, the U, the D, the S. Okay. So at this scale, we can describe the standard model dynamics in terms of an effective standard model Hamiltonian for just describing delta B equal 1 processes. So here we're looking at delta B equal 1. Actually, delta B equals minus delta S equals 1. And in general, we can, let me write it more to the side so I have more space. So H effective standard model for delta B equal 1. In this case, I can describe it in the following way. There is a prefactor which I can parameterize in terms of the Fermi constant. Okay, so since it's a weak process, there will be a CKM prefactor, which I know now will be dominated by VTB, VTS star. And then I have two sets of operators which are generated at this scale. One are so-called electroweak operators. So they come suppress the factor of electromagnetic structure constant over 4 pi. So they contain, if you want, the Z penguin and the photonic penguins. So I write them, so there's this prefactor alpha over 4 pi times the sum of the effective Wilson coefficients and the operators. And these are conventionally labeled as the 7, 9, and 10 operators. Okay, and let me write them down explicitly. So O9 is given by SL bar gamma mu BL L bar mu L. Here I'm keeping L as a general lepton flavor. First of all, because in the standard model, to a very good precision, all electromagnetic weak and strong interactions are lepton flavor universal. So it's exactly the same expression up to tiny corrections for all lepton flavors. And later, because we were considering actually two different decay modes of two different lepton flavors. And so this operator, or in particular the relevant Wilson coefficient up front, receives loop contributions from W, Z, and photon exchange. So this contains the W box, the Z penguin, but also the photonic penguin. So the same diagram as I drew before, but with a photon, okay? Just with a vertical photon, which then couples to a pair of leptons, okay? You can see this because this is a vectorial leptonic current, okay? This will be very important in a minute. Then we have the O10, which is given by SL bar gamma mu BL and then L bar gamma mu gamma 5 L. Now you see these two operators look very similar, except that here we have the axial current on the leptonic side. So we know that this operator does not receive contributions from the photonic penguin. So this only receives contributions from the W box and the Z penguin. There is another important distinction, is that if we look at the decay B sub s to mu plus mu minus, since that is a decay where a pseudoscalar meson decays to a pair of leptons, the current that contributes to the hadronic matrix element is only the axial current. Okay, so in B sub s to mu plus mu minus, while it seems to be a very sensitive probe of new physics, it only probes the O10. It's completely transparent to O9, for example. Okay, so here we have the hope that we could also, for example, test new physics which comes in the form of O9 operator. Then we have also the O7, okay, O7, which is of the form mb over E times SL bar sigma mu nu BR F mu nu. Okay, this is the flavor-changing photonic dipole operator. It describes the emission of a photon and an S quark from a B quark. Okay, a flavor-changing photonic interaction. It will contribute to B to S mu plus mu minus because the photon can be a virtual photon and then convert to a pair of muons. Okay, so it contributes to this decays. Okay. Then, in addition to these, so these are all have intrinsically weak strength, okay? Because they come from weak loops, and they're mediated by the WZ and the photon. But there is another class of operators which don't have this suppression, and they are usually, okay, we can again write them as CIOI, but now I, by convention, this goes from 1 to 6, and then there is the 8, okay? So you see, altogether they would have operators from 1 to 10. Now, the structure of these operators is very different. So these OI, in fact, they carry a quark flavor index. So you have a Q here, and a Q here, and there's also a Q here, and the Q runs over different quark flavors, all the dynamical quark flavors. And if I just write the QO2, or no, I can actually write them in general, OIQ. In general, they will have the following form. I will have the Q bar, some Lorentz structure, B, contracted with the S bar, some Lorentz structure, Q. Now you will see immediately that if Q is an up-type quark, this is actually an operator which appears at the tree level. So this is nothing else but a single W exchange contribution which generates a 4-quark. These are 4-quark operators. Okay? So you see there is no loop suppression of those. Here we had a loop suppression, a weak loop suppression. Here it's just a normal weak strength suppression. Okay? So why are these relevant? Since we're considering semi-leptonic functions, why the hell am I writing those down? We'll see immediately. And why I didn't bother to discuss them when I was discussing the K2 pi nu bar or B to mu plus mu minus. And the reasoning is the following. I'll write it very schematically. So if your final state is a kaon and a pair of leptons, and now you want to compute the matrix element where you insert your effective Standard model delta B equals 1 Hamiltonian B, and of course you still have the whole QCD and QED Lagrangian present in your theory. I didn't write them down, but it's there. So you can schematically write this as there will be a leading order, just a single insertion of all the operators where your final state, where the external states contain a B quark, an S quark, and 2 leptons. They will contribute at leading order. So those are simple to compute, okay? But then there will be another set of contributions which will be of different form, which will actually be a 4 quark operator where you close the quark loop on the other side. You emit a photon which is still present in your theory. There is no Z boson, but the photon is still there. So you can emit a virtual photon which then splits into an L plus L minus pair. Okay? And you see immediately the problem that arises is that while these are described by local matrix elements, which we can then write in terms of form factors and try to evaluate on the lattice, this thing is a non-local matrix element. Because these quarks running in the loop are light quarks. They are up quarks, charm quarks, which are below the B meson scale. So they can actually form, they can rescatter, they can form bound states. And so they induce a non-trivial Q-square dependence of your, in practice, of your matrix element. And so they're much, much more difficult to evaluate. Okay? So they are long distance, non-local contributions. And they have a Q squared, which is just the PL plus PL minus squared. So the sum of the lepton momenta squared. They have Q squared dependence. Okay. Beyond the form factors. So the local matrix elements one can compute on the lattice. This is, and we can also understand why we didn't have to consider those in these decays. So in the case of K2 pi unibar, since our final state contains only neutrinos, neutrinos don't couple to the photon, okay? So these are absent. And in the case of B sub S and B sub V to mu plus mu minus, the final state muons have to be in an axial current. So again, they don't couple to the photon, okay? So that's why we can predict precisely those decays, and we don't bother about long distance. These are called also the QCD penguins, okay? Or photonic, well, this is a mixture of like QCD photonic penguins. And there is quite a vivid illustration of the consequence of the presence of these contributions in the case of B to K star mu plus mu minus. So here I'm plotting a sketch of the spectrum of the B to K star mu plus mu minus decay as a function of Q squared. Okay? And we can roughly distinguish 3 regions in this decay mode. First is what it's usually called the low Q square region. So the low Q square region has 2 features. First is that at very, very low Q squared, what happens is that we have a steep rise of the decay rate, which is simply from the fact that that O7, which is basically just an emission of a photon, this photon, as Q squared goes to 0, the photon becomes more and more on shell, so it starts to dominate. It has a 1 over Q squared pole, okay? And this pole is only regulated by the leptonic mass at some point, at very, very low Q squared. Then, in the next region, there is the region where the rate is dominated by these 2 operators, the O9 and O7, and their interference. And this is also the region where, I have it written down, yeah. So, q square smaller roughly than 4 times m charm squared, so this contribution can actually be estimated. Why? Because these quarks can never go on shell. Okay? If I have C bar intermediate state, which is the one which is problematic in B2S transitions simply because it's not CCAM suppressed compared to the dominant top loop, contrary to the UU bar, which is CCAM suppressed, so we can neglect it to a good precision. The CC bar, which is there, this loop never goes on shell, so there's no stronger scattering possible. There are no intermediate on-shell states which I could form. So I can actually, there is a systematic way to compute these non-local effects in perturbation theory, and this goes under the name of Qcd Factorization, okay, where I basically reduce this matrix element roughly to a function of q squared, which I compute in perturbation theory, and a set of, now again, local matrix elements. And these I can then compute with lattice QCD. They're the form factors. Okay. Yeah, so there are no absorptive CC bar contributions. Okay, this is why it's possible. So this is the region where we have most theoretical control, and we can actually do predictions of the rate, if we know the relevant form factors, of course. Now then, the second region becomes much more problematic, because as soon as the q square rises in the region where CC bar can form bound states, then what happens is I produce narrow CC bar resonances. So this is the J psi, the J psi 2s, and then all the other resonances. Okay, and in this vicinity, there is this factorization is severely broken, and there is I have no theoretical control, so I cannot compute. I don't have any means currently to theoretically compute this rate, in this rate. However, when q square goes further up, when I go beyond the narrow resonance region, then what happens is that if what remains is a set of very broad resonances which populate the high q square region. So this is where these CC bars start to have large relative momenta. So they don't anymore form narrow states, they form a very, very broad state, and there are many of them. So if I integrate over this region, there are some reasons to believe that one can actually regain theoretical control. So there are also theoretical estimates on this side. So in the very high q squared, not for the q squared dependence, but for the total rate in this case. Okay? So we can never actually compute precisely those wiggles, but if we integrate over them, we actually average over them, and then we can have some theoretical control. And outside, the techniques to do that are actually operator product expansion in this region of 1 over q squared expansion. Okay, so in practice then, we could in principle we cannot compute the total rate for this decay, because we have this narrow resonance region. We could try to compute the rate in the regions where we can compute, so in the low q squared and the very high q squared, and there the main limiting factor is the knowledge of the form factors. Okay? In particular, in the case of B2K star, we have to compute, again, this is a 1-to-1 matrix element. The complication is that the K star is unstable. It decays into a K pi final state. And this is not a weak decay, it's a strong decay. Okay? So while it seems that this is a 1-to-1 matrix element, in fact, it's a 1-to-1 star, because this is not a stable particle. So effectively, to have really theoretical control, one would actually have to compute 1-to-2, which, as you know from yesterday, is much, much more challenging. We barely have any control in K2 pi pi system. It's much more difficult if you try to compute now B2K pi in the K star resonance region. Okay? So we cannot really rely on the rate or the differential rate. They have sizable uncertainties. So let's go back and try to see if we can gain more theoretical control by actually just looking at the angular distributions. Okay? And in fact, there was hope that this is so. Especially since in this region where one can use Qcd factorization, it was shown that certain ratios of these angular helicity amplitudes, in certain ratios, the theoretical effects of the form factors actually cancel in a certain limit. In particular, I would just write one such ratio because it's phenomenologically the most interesting at the moment. It's called the P5 prime, which is defined just as the S5. This is this S5 here. So it's just coefficient in front of one of the angular distributions normalized to the product of the square root of FL times 1 minus FL, where FL again is just a coefficient in front of another linear combination of angular distributions. It turns out that in the limit where MB goes to infinity, the leading form factor dependence cancels in this particular observable. Okay? Yeah, so actually it's more precisely it's the MB and also, unfortunately, MC goes to infinity. Okay, which is not a very good approximation, it turns out. And so why I'm telling you this, because if we look at now the comparison of theoretical predictions for this particular observable as a function of Q squared to the various measurements, so it seems like the measurements are not very clustered together, but actually the significance of those measurements is completely, at the moment, completely dominated by the black crosses, which are the LHCb data. So you really should focus on this particular band here, where you see the black cross, which denotes the measurement, seems to be quite off from the theoretical predictions. So the theoretical predictions are in the boxes, and so using two different sets of form factors, because they, of course, once one goes beyond this limit, there is some residual dependence on the form factor, so there is some theoretical uncertainty. But you see there seems to be a disagreement between data and an experiment. Now, of course, this looks interesting, but due to all of these long distance trouble, we might remain skeptical and look for other observables which might be cleaner theoretically and still show some sensitivity. And in fact, one interesting idea is to use the following observation, that all the long distance contributions, in fact all the standard model contributions, are almost completely lepton flavor blind. Okay? So all standard model contributions to this decay, in particular also the long distance ones, so due to the photon and the CC bar intermediate states, are lepton flavor universal. Okay? And of course, this is also true in the standard model, the short distance contributions. So the Z and the W. The Z penguin and the W box are also lepton flavor universal. So one can consider a ratio a lepton-flavor universality ratio denoted as RK star in the bracket, so we can do this for either B to K or B to K star. And we define this ratio as in a region of Q squared, so going from Q squared minimum to some Q squared maximum. Why this is useful? Because we don't want to go over the narrow resonance regions, because there the effect will be completely dominated by B to K J psi, or B to K star J psi, which is uninteresting in this context. So this will be just the integral of from Q square min to Q square max of the differential rate of the B to K star in parentheses mu plus mu minus over the same rate but measured in the E plus E minus channel. Q squared min to Q squared max d gamma over d Q squared of B, this is dq squared, B to K star E plus E minus dq squared. And as I already told you, in the standard model, this ratio is expected to be very close to 1, as long as we are away from threshold, where, of course, kinematical lepton mass effects are very important. So we can, there is a very precise prediction, for example, that RK and RK star in the region between 1 and 6 GV squared. So this is actually the region where we also have good theoretical control, and this is also the region where there seems to be a deviation in P5 prime, should be 1 up to corrections which are of order of per mil. Okay? So contrary to the previous observables in B2K and B2K mu plus mu minus or E plus E minus, this is an extremely theoretically clean observable. Okay? Now, LHCb went and measured this, and I only show you the results for the K star, and the result for the RK looks very similar. In particular, if we look at this bin between 1 and 6 GV squared, it seems to point to the experimental value, which is below 0.8. Yeah. Mm-hmm. Then, yeah, of course, if we choose Q square minimum to be the threshold, then they will be different. But then we also don't expect this to get 1. So we only get a very precise prediction of close to 1 if we choose Q square min and max the same in both cases and away from thresholds. So that's why I chose 1 and 6. Sorry, is? Yeah. It's the one I choose. No? So in this case, they chose 1 for the Q square min and 6 for the Q square max. They also, for some reason, they also measured the same ratio in the very low Q square region, where you see the prediction is not for the standard model, which are those small points, is different from 1. Because in this very low Q square region, the muon mass effect starts to show up. Okay? So you don't expect this to be 1. But in the 1 to 6, this is 1 to per mil level, while the experiment seems to suggest otherwise. So let's see if we can have some implications from this. We can derive some interesting results. Okay, so it seems that in this case, the standard model theory is solid. So what we can conclude is that the experiment seems to suggest that RK star, between 1 and 6 GeV squared is smaller than roughly 0.8, while the expectation is order 1. So this is, in fact, an order 20% effect. Okay? Now, you could, first thing you can check is that, well, maybe since one contribution which is present here is the Z penguin, maybe the Z couplings to leptons are non-universal. But in fact, those have been checked at lab, and the rates of Z to a pair of leptons have been checked, have been measured, and found to agree to a precision better than 1%. Okay? So this cannot be due to the Z. So let's consider what kind of new physics this could be if the measurement remains. So, and then among the operators that I wrote down in the beginning, there is an operator which would fit the requirements, and this is precisely the Q bar. Let me write the flavor indices on top for now. Gamma mu, Q2, L bar 2, gamma mu, L2, where I've chosen, so this, of course, the value of the indices, if I want to relate them to physical flavors, I need to specify the basis. Here I've chosen the basis where the down quarks and charged leptons are in their mass basis, so the mass basis of down quarks and charged leptons. If I have this particular flavor structure of this operator, this will induce precisely a contribution to O9. Okay? And now O9 is a good candidate to induce such a flavor relation if it only contributes in the muon channel. Okay, that's why I chose L2 here. And in particular, if I do the simple estimate, I get that the relevant scale of this operator, which would induce a 20% effect in RK, this would be over Y. This is the operator QL1 BS mu mu would be roughly 40 TeV. Okay. Now, as I told you, if I have generic flavor structure, of course, I don't necessarily expect the first effect to come in the B sector, but in the kaon sector. So another, perhaps even more interesting estimate is generic flavor structure. I assume something which is minimal flavor relation like, or respects a U2 approximate flavor symmetry. Then this scale is reduced by a factor of square root of VTS, and this would then be an estimate of 8 TeV in MFV or U2 models. Okay. So the relevant scale here is around 8 TeV for flavor protected models. Okay, so since I still have some minutes left, I can discuss a related effect. So to make full circle of our study of flavor structure in the standard model and beyond, now since there seems to be hints for lepton-flavor universality in flavor changing neutral currents, let's go back and test this in the charge currents. So let's consider lepton flavor universality in charge current mediated B decays. In particular, we will consider B to D or D star L nu decays. And in particular, these decays are used to extract the VCB matrix element, as I told you in one of the previous lectures. So for lepton being a muon or an electron, these are used to extract, this is one way to extract the modulus of the VCB matrix element, CK matrix element. And as I told you, this extraction seems to be perfectly consistent with the other measurements constraining the CKM, both at the tree level and at loop level. So there seems to be no indication of anything going amiss in these decays. Okay? So at the quark level, these correspond, of course, to a transition B to C L nu. Now, to just discuss them. So the main theoretical uncertainty in predicting the rates of these decays, again, comes from the hadronic one-to-one matrix elements. Here describing the transition of the relevant hadronic charge current between the initial B meson and the final D or D star meson. And there are, again, they can be parameterized in terms of form factors. Okay? So again, these are form factors. They can be computed using lattice QCD, and they're currently known down to order a few percent, down to order percent. So why are these much better known than, for example, B2K or B2K star? Because the way they are actually computed, they actually compute corrections to a limit, which is the MB and MC goes to infinity limit. In this limit, one can actually predict the form factors exactly. And so, because in the limit where the B and the charm quark masses go to infinity, this is a conserved current. So we know the normalization of a conserved current is just one. The form factor is just one. And so what they do on the lattice, they just compute corrections to this. So the corrections, of course, have a bigger uncertainty, but because they are small in absolute value, then the final uncertainty of the form factor is small, much smaller than in the case of B2K, for example, or B2K star. Okay, so this seems to be theoretically clean decays and also seem to agree with the standard model. So what we will consider are, oh, maybe I should write up there. Sorry. Is again a lepton-Flavour universality ratio except that this time the more interesting ratio that was actually measured and one can also predict is not between the muon and electron channels, but the following. So the observables are called conventionally RD and RD star, and they are defined as the rate of B to D or D star tau nu over the rate of B to D or D star L nu. Now L nu means different things for different experiments. So L nu means E plus mu for the B factories, so for the Bell and Babar experiments. Of course, Bell 2 doesn't have a result on this yet. And it only means muons for the LHCb. For LHCb. And again, this ratio is a test of lepton-Flavour universality, but now in the charge currents. In the standard model, contrary to the RK and RK star, RD and RD star is not 1, it's smaller than 1. And this can be easily understood because the phase space effects here can never be neglected, because the tau mass is not small compared to the B mass. So we have sizable phase space effects. And those can be actually computed exactly. Can be computed exactly. But there is an additional effect, which is they are non-negligible m tau over mb squared suppressed contributions to the decay amplitude. Contributions to decay amplitude. In the case of B to K mu plus mu minus, those were m mu over mb, so we are completely negligible. In this case, they are not, and they result in a single additional form factor, which is not present or is completely negligible in the case of B to D star L nu. So there is one additional form factor, and those contributions don't cancel in the ratio, in this ratio. Doesn't cancel in the ratio, contrary to the effects of all the other form factors and contrary to the RK or NRK. But again, this form factor is known exactly in the heavy quark limit, in the infinite heavy quark limit, and must be computed. So those corrections must be computed, again, using lattice QCD and heavy quark effective theory. So the leading effects can be computed in the limit, and then lattice QCD can provide more precise estimates. The result of this is that, that RD and RD star are actually known quite precisely in the standard model, even though they're not one. So RD star in the standard model are known to order few percent, and the measurements seem to show a rather curious picture. Okay, so this is a pendulum of experiments in the plane of RD and RD star. We see the results of all the three experiments which have measured these decay modes or these ratios. The standard model expectation is down here with a tiny percent level error. And the two ellipses, the blue and the black ellipse, are the combined measurements of RD and RD star by Bell and Babar respectively, while the LHCb has currently only measured RD star, and so the LHCb result is this cyan and red vertical band only. We see that when one combines all these measurements, one arrives at this red ellipse, which shows the 1 sigma confidence region, and the standard model actually seems to be almost 4 sigma away from the average of experimental results. So what to make of this? I'm running out of chalk. Here. Okay, so to make it very short, so the current experiments, okay, suggest that they differ from expectations in the standard model by roughly 30%. Okay, so this is a 30% effect. Again, the first thing we can check is whether this could be an effect of lepton-favored non-universality of W couplings. Okay, so one can check the lepton flavor universality of W decays, and this has again been measured at lab, and in particular, the ratio of W decays to tau nu versus the W decays to L mu, E mu or mu nu has been, so those agree at few % level. Actually, there's a small tension, but it's much, much smaller than this 30% effect. So this cannot be due to a W, okay? Cannot be a W. Like previously, it could not be a Z or a Z penguin. In this case, it cannot be the W. So again, we need to look if this is really the real world. There has to be a contribution beyond the W contribution. So if we can go back to our effective new physics Hamiltonian contributing to delta F equal 1, and we also had there, I've written on purpose, an operator which actually does contribute also to charge current flavor changing processes. And the relevant, so this is an example of new physics which could accommodate this. Example, new physics, the relevant operator would have the structure Q3, gamma mu, TA, Q2, and L3 bar, gamma mu, TA, L3. Since here I'm contracting to SU2 triplet currents, this operator will induce both flavor changing neutral currents, but also flavor changing charge currents. Okay? And so it will contribute to precisely to these decays, and one can estimate the relevant scale of this operator that could accommodate these anomalies, and it turns out to be extremely low. It's only 3 TeV. Okay? Again, this is for generic flavor structure. If I now impose furthermore that this whatever causes this operator should respect approximately the standard model flavor symmetry, so it should be approximately minimal flavor violating, then this scale is further reduced by a square root of VCB, and then the relevant scale for such new physics is as low as 500 GeV for MFV like models. Okay, so this is completely in the LHC territory. Okay? Yeah. So this would be a natural model with generic flavor structure, so all the Y's are equal. But we know that this will probably completely fail because it will produce effects in other charge currents, like in K2 pi L nu and leptonic decays of charged D mesons and all sorts of other effects, which we don't observe. They seem to be consistent with the standard model. So one has to invoke something like third generation alignment, which is like a U2 model or an MFV-like model. But then this immediately means that has to be, the scale is even lower, so we expect some new physics below the TeV. Okay, so I will stop here because I ran out of time. So at the end, just be aware that these last 2 topics about the so-called B anomalies, okay, so both of them are called conventionally nowadays as the B anomalies, is something which is ongoing work both by the experimentalists and the theorists, and is of course, can change at any conference. Okay, thank you. Are there any questions?